everyone. Here we are now with our guest, Felix Büchi, and he has done a technology assessment of our technology, and we will talk a little bit about that and about your conclusions. But could you maybe first say a few words about yourself and your background?
I'm a chemist. I have been working for a Polscher Institute for the past more than 20 years, and past 10 years also in PEM electrolysis. I mean, we have developed structures and materials for this technology.
We are running our system with 0.1 or sometimes 0.2 milligrams of iridium. Where would you say that competitors are today?
I mean, today there is, of course, many developments to go to low iridium loadings for PEM electrolyzers. I would say the performance I have seen from Smoltek technology is matching the best performance in this field.
Are you comparing to companies with the same amount of iridium loading that we have, or is it?
I mean, there's not easy to compare because, I mean, there is many differences in preparation and materials. But I would say what you show me with 0.2 milligrams matches, I mean, the industry standards with 1 to 2 milligrams with same components and boundary conditions.
Do you mean that when others use 1 to 2 milligrams, we do it with 0.1, 0.2?
Yes.
When we try to explain about our technology, we tell people that iridium is extremely expensive, and then we get the question back, maybe this can work or that can work. Can you say some words about that?
I would say at the moment, iridium oxide is the only known stable catalyst for PEM electrolysis anodes. So, of course, there is also research on that, and it's not completely impossible. Other solutions will be found, but not for the moment.
Why are so many people trying to find a solution to use something else than iridium?
Yeah, because iridium is like 4 times more expensive than gold, and only 5 to 7 tons per year is mined. So it would be very attractive to have an alternative to iridium. Yeah.
And when it comes to producing hydrogen, there are methods where you do not need iridium.
Yes, there is other electrolysis technologies which do not require platinum group metals as catalysts, but they have other disadvantages, such as slower startup, larger footprint.
Yeah. Could you say a little bit about the technology competitors are using?
There is different approaches to, reduce the iridium requirement for the anode in PEM electrolysis. One of the promising other approaches is to use core shell particles, where the iridium or iridium oxide is the shell on an inert particle. And of course, this then, because in electrolysis, only the atoms at the surface of the particle are used for the catalysis. I mean, this reduces a lot the amount of iridium required.
So can you explain a little bit, if you have particles, it's not that easy to reduce iridium as if you have just a surface instead?
There, for such an embodiment, which is called catalyst layer in PEM electrolysis, there is different requirements. There need to be porosity, there need to be conductivity, electronic conductivity and ionic conductivity. And so, because the electronic conductivity comes only from the iridium phase in these catalyst layers, then the reduction of the iridium can cause problems.
What do you see as the main achievement with the solution Smoltek has developed?
The main achievement, I think, is to reduce the amount of iridium not going to nanoparticles, but to a nanolayer. I mean, this is unique.
And when you say unique, in what way?
In these electrochemical techniques, electrolyzers or fuel cells, I mean, the typical approach to maximize the utilization of catalyst is going to nanoparticles, so very small particles with diameters of very few nanometers. And the Smoltek approach, and this also this maximizes the nanoparticles, maximize the atoms at the surface for a given amount of material. And in the Smoltek approach, by having a base layer with a high internal surface where the two-dimensional catalyst layer is put on, this makes an intrinsic difference.
What do you mean with a conductive base layer?
Yeah, that the carbon fibers coated with platinum you use as the base layer, I mean, provides an electronic contact to all of the catalyst.
All particles that, or atoms, or what would you say, that we put on our fibers, all of them are in contact with electric current.
Yes.
When we try to explain to customers and other researchers and so on what we are doing and why we do this, we often talk about that we get a much larger surface area when we use carbon nanofibers than if you place it on a flat surface or in a membrane. Why is it important with the surface area?
Because to have technically reasonable current densities, you need to have more than a higher surface per surface of catalyst. Otherwise, you cannot generate the required current density. So, I mean, the water is split into hydrogen and oxygen on that surface.
Okay. And why is it important that you have a large surface area for that to happen?
Because the rate at which the water is split on the catalyst is not infinitely fast. So there is a certain turnover per catalytic site. And to use enough current, so you need a high surface. And that's why you combine this high surface into a small macroscopic volume.
Okay, so what you say is that we make it possible to place very much iridium available for splitting water, but on a small surface.
Yes, you provide a high surface for the iridium for the splitting of water.
Okay, and what does that mean? Why is that important?
The high surface is required to achieve high macroscopic current densities, which is required to have an electrolyzer of an attractive size. The higher the current density, the smaller the electrolyzer for the same amount of hydrogen produced.
Maybe the most important question for us and our shareholders to understand. What is the main advantage from your point of view with Smoltek's solution? And how do you compare that to what others are doing in terms of performance?
The main asset of the Smoltek solution, and this is unique, is to be able to prepare a low amount of iridium onto the PTL. Because you are able to prepare a high surface area on the PTL.
And how are others trying to solve this?
So today, it is a bit of a consensus that it is much easier to prepare on the membrane because it's a flat surface rather than on the PTL.
So why is that an advantage?
On the membrane, in the flat surface, all the catalyst is there. When you prepare on the PTL by spraying or slot die coating, part of the catalyst will go into the pores and disappear for the electrochemical activity.
And when you look at Smoltek solution, do you have that problem as well?
No, Smoltek solution provides a increased surface on the surface of the PTL. The iridium is placed right at the surface, which is then the interface to the membrane. And because this surface is made conductive, so most of the placed iridium will be active.
One of the studies that our R&D team had done was to run a complete electrolyzer cell for 1,000 hours. What could you conclude from that?
And from the results I have seen, there is a bit an untypical behavior that there is a degradation in the first 10-ish hours, but then for the remainder of the 1,000 hours, the performance was stable.
The problems in the beginning, what do you think that could have been?
This could be like chemical problems. The catalyst is dissolving or changing, and there could be physical problems. That could be like detachment of the catalyst from the membrane or things like that. And I have seen that when you only measure the electrode in a liquid electrolyte, the performance is very similar at the beginning of life and at the end of life after 1,000 hours. So the reasoning would be that there is some physical damage to the electrode in the first 10 hours.
So what does it mean that there are physical problems in the beginning?
There can only be hypotheses. What is the reason for that? But considering how the electrode is made, it could be that the oxygen pressure evolving in the electrode could detach the membrane from the electrode, and so the first 10-hour disactivation comes from this detachment process.
So what you mean is that the membrane and our electrode don't really stick together?
If this hypothesis is correct, that there is this detachment causing the beginning degradation, then one can think of several solutions on how to work on that.
Finally, I would just like to ask, what do you see as the main achievement with the solution Smoltek has developed?
From the results I have seen, your cells with 0.2 milligrams, when they are compared to cells with the same materials, same conditions, with much higher iridium loading, the performance is still the same.
Yeah, that is what we try to do. So I just want to say thank you very much for having, for that you did this assessment about our technology, and also that I'm allowed to talk to you here. it's very extra valuable because we are working with customers today, but we are not allowed to mention who they are. So we need someone like you who have sort of been in this world all your life and knows everything there is to know about PEM electrolyzers and the cells. So when you say that it's unique and it works better than what you've seen before, then we are very proud. So thank you very much.
Thank you, Ellinor. It's a pleasure.